Now, having been done with glucose, we move on to fructose. Now, fructose, like glucose, is also a monosaccharide. And what was a monosaccharide? Any carbohydrate which cannot be hydrolyzed any further was known as a monosaccharide. Okay, now if I want to draw the structure of fructose, so let us draw the structure of fructose. Now, in fructose, the group present is the ketone group, the functional group present is the ketone group, and accompanying it at the top position is our CH2OH. Also, please note that at the bottom also we have a CH2OH, and next we have to fulfill these three valencies with the OH and H. So now what do? We know that leaving this, the first chiral carbon, leaving this one aside, the rest of them will have OH on the right. So let us draw OH on the right, and the first one, the OH, is on the left hand side. Okay, the rest of the valencies let us satisfied with hydrogen. So now we have our structure of fructose, and this structure of fructose, since the OH is lying on the right hand side of the last chiral carbon, we can call this the D-fructose. Okay, so let us move on to the basic that we wanted to cover. And what was that? To make this open structure go into the cyclic form. Now, since we have done glucose, we know now that these cyclic structures will exist in equilibrium with our open structure. So this is fructose. If I call it more properly, we can call it D-fructose. Okay. So now let us move on to the cyclic form. So how do we do the cyclic form? The lone pair of oxygen of this last chiral carbon are going to attack the carbonyl group, the C of the carbonyl group, and what are we going to observe? We're going to observe a negative charge being developed at this particular chiral carbon. So at this ketonic group, the carbonyl carbon will get negative charge, and this OH, since it is losing a lone pair, will get a positive charge. So if we have to draw, so what are we actually going to get? If let us see, firstly, what we observe is that we're going to start with naming the carbons. So 1, 2, 3, 4, and our fifth, we're going to call the oxygen atom as the fifth molecule of our ring, because that is the lone pair which is going to attack our carbonyl carbon. So now this lone pair will attack this carbon. So let us come to our cyclic ring now. So in the cyclic ring, I know that we're going to have an oxygen atom, that is this particular lone pair of electron in oxygen. So this oxygen will have center position over here. Now let us start by naming the carbons here also. So we've got 1, 2, 3, 4, and the fifth was already oxygen. Okay. So now this fifth is attached to the first one, and this first one is carbonyl carbon. So now what we know is that we're gonna have two valencies over here, and these two are gonna be fulfilled by either CH2OH, that is over here, or it is gonna be fulfilled by this O negative. This C double bond O was getting a negative charge because of the lone pair, because it was attracting the lone pair of electrons. So let us just see if this had a negative charge, and we know that since this particular O, oxygen with a lone pair, was losing this lone pair, so it was getting a positive charge. Now what happens is that, let us just write to fulfill the valency first. So this is what I'm getting at the fifth and the first positions of my ring. So what do I observe here is that this particular H and this particular O, they can get a proton transfer done. And what happens when a proton transfer is done is that our H with a positive sign will disappear from here, and it will come and join this O and neutralize the negative charge. So we have a proton transfer over here, and this proton transfer helped us to neutralize this O negative and this H positive which was lying over here. So now we have the fifth and the first position decided. So let us move on to the second carbon over here, this one. And in this, we note that this OH has to lie either over here or over here. Now, what we're going to do is we're going to make this OH come at that position which is trans to our CH2OH, so that there is less hindrance. So we have got an OH over here, we've got an OH over here, and the second valency is fulfilled by H. Now, let us move to the third carbon over here. And in this third carbon, we note that the previous OH is lying at trans to this next OH that we have. So, what are we going to do? We're going to place an OH at trans to the previous OH, and H is going to come at the top. Also, in the last one, we note that we have got now two groups. One is the CH2OH and one is the H group at the fourth one. Okay, so what we're going to do is that we're going to place CH2OH group at trans to this previous OH, so hindrance is less, and we have got a CH2OH group here and H is accompanied here. Now, what we notice is that this first chiral carbon that we are actually, this first carbon of our ring, here this carbon actually is a new chiral carbon which is formed. So, a new chiral carbon is formed. So, this new chiral carbon, we can have this particular groups, these two groups which are at C1, they can exchange the position. So this CH2OH can go at the top and also this OH can come at the bottom. So our next cyclic figure will have a little differentiating factor from the previous one, and that will be that the OH will come downward at the downward side and the CH2OH will be at the top. The rest of the molecule looks exactly the same, so we just complete it as it was. So you just copy paste it from the previous cyclic figure, and the only point of difference is our CH2OH group. So this CH2OH is lying here and this one is lying over here. So what are we going to do now is we're going to see their positioning, and what we notice is that this CH2OH is lying at trans with this OH, and this OH is lying at trans with this OH. This OH is lying at trans with this CH2OH. So in this particular cyclic figure, all the CH2OH as well as the OH are lying trans to each other. But if we move on to the second one, we notice that this particular CH2OH is at cis with this OH. The rest of them are trans, but what we wanted all along was to check whether which one is the trans and which one is a cis. So in the first one, I noticed that all the OH and CH2OH are at trans to each other, and therefore this becomes the more stable form, and thus we call it the beta form. And now here in this particular one, leaving all the carbons aside, the C1 is at cis with position with the C2. So CH2OH is at cis with OH, and thus we call it the alpha form. So what we learned here is how to differentiate between the beta and the alpha form is that the positioning of this OH and the CH2OH group, if they are trans to each other, we call it the beta form. If they are cis to each other, we call it the alpha form.